Hi, this video we're talking about a new concept called the thermal expansion. This is something we experience every day. In the summertime, you see the concrete expand, right? And wintertime, you see it contract, and then you see a lot of cracks on the road. And all those are due to the temperature change and make it expand and contract, and so we have this thermal expansion and the thermal contraction. So in order to deal with that, we're going to introduce a new concept called the thermal expansion coefficient. So it's called alpha. Let's write it down. And this information can be found in your inside back cover. Every material gonna have their own thermal expansion coefficient, just like elastic modulus or Poisson's ratio, etc. And that has a unit of per degree Celsius or per Fahrenheit. Okay, and here I want to make sure this degree Celsius and Fahrenheit, they means delta T. That means it's a temperature change. Because of that, we know if it's temperature change, if it's delta T in degrees Celsius, it's going to be the same as temperature change in Kelvin. The same likewise, delta T in Fahrenheit will be the same as delta T in Rangin, right? So knowing that, that's our thermal expansion. Now, the next concept I want to go over is called the thermal strain. Just like we learned about strain previously, is how much deformation happened per original length. So thermal strain gonna have a relation. It's gonna be epsilon strain. I'm gonna add a T. That means due to the thermal, and that's gonna be equal to alpha, this thermal expansion coefficient, times delta T. Okay, think about the unit. Alpha is per degree Celsius and delta T is in degrees Celsius. So they cancel out. That will be unitness. And we do know this is no unit for strain. Then the third concept we want to go look at is called the thermo deformation. Means how much actually elongation or contraction happened due to the temperature change, right? That's delta deformation. And we're going to add a T, indicate it's thermo. So we know here is epsilon. Epsilon is deformation over original length, right? So knowing that, we can certainly find out thermal deformation equation. That's going to be equal to epsilon T times original length. And substitute the thermal strain, which is alpha delta T, then times L naught. That's also, I want to make a note, L naught is original length. Okay. So far we're talking about thermal strain, and from there we come up with the thermal deformation. The last concept I want to go over is called a thermo stress. All right, so in the elastic region of material, we know they abide by this Hooke's law, which means the stress sigma is going to be proportional to the strain, and the slope is this elastic modulus. And because of that, we can go ahead, write it down. The subscript thermal stress is due to this thermal strain, and then we can have an equation for sigma T, which is thermal stress. So elastic modulus times epsilon right here, alpha delta T. Then we have expression for thermal stress. Okay, so that's for this video. Very clean cut of the thermal expansion. And in the next video, we'll look at example and directly apply for this concept. All right, I'll see you at the next one. Take care. Bye.